Thank you, Jamal, and this opportunity. Initially, I thought I would talk about the AI and quantum computing for science and engineering, but I want to add another topic. So the first part, I will talk about the enhancing quantum annealing in digital analog quantum computing. And after that, I will talk about AI. So it's kind of variation of the digital analog quantum computing, but a little bit different from the Michel's approach. So I will introduce first digital analog quantum computing. And in addition, I combine the two concepts, the counter-diabatic driving, which is one of the inventor, Del Campo, supposed to join this conference, but unfortunately he couldn't. And I will introduce our method and share the results. Okay, again, what is the digital analog quantum computing? In my basic understanding is we can realize the CNOT by easing interaction. That is a concept. And what is a counter-diabatic driving is we add the extra term, here, the HY, which is in this case, there are many approaches, but in this case, this is a non-uniform field in Y, and we have the scheduling of three terms with the cost function and transverse field and Y field. So combining those two components, so let's think about what is the role of the counter-diabatic driving term. So without counter-diabatic driving, if the transverse field changes or decrease gradually and increase the host term or the Z field, if the change happens very quickly, the system can't follow the ground state, temporal ground state of the dynamics. But we can help to follow or to have the much more higher fidelity if we apply the counter-diabatic term. This can be utilized for sensitivity analysis if we assign the counter-diabatic driving in a right direction. In this case, this is minus Y. We'll have the low energy state. But if we apply the wrong direction, we'll have the high energy state. So we can decide by measuring the energy difference between two trials. So we propose the algorithm called quantum grid optimization. And this is basically utilizing such sensitivity analysis one by one for each qubit. And it actually works for small annealing time, like tau equal 1 or 5. We see a good improvement compared to the simulated annealing or quantum annealing. And yeah, this is actually the curve improved with a good success probability in terms of if we increase the size of the program. And this is a log scale. And if we plot in a linear scale, yeah, so it's not so impressive. And what is this line here? So I introduced a sensitivity analysis calculating by energy. But if we measure the fidelity, in this case, optimization problem, we can't, we don't know the fidelity. That is what we need, the exact solution. But if we measure fidelity or we know the ground state, the success probability is always 100%. That means that what observer will be applied for sensitivity analysis is important. So I thought that this is a time to calculate the output of the quantum annealer by the by quantum circuit. I mean that this is the another a little bit different concept of the digital analog quantum computing. We first generate the state by quantum annealer with counter derivative driving, and followed by the quantum circuit to measure the energy or other observables. So this algorithm one calculates the energy, the difference of the energy approximately, and I will show another algorithm circuit. This is try to measure the energy difference more accurately, but we need the controlled quantum annealer, which I don't know how to implement. And we need 4 components here. So we basically need or repeat the quantum annealer 4 times with control. That should be difficult. But if we actually we can simulate on the computer. Okay, this is algorithm 2. And 3 and 4, as I mentioned, that not just energy, but other observer may improve the performance. So in this case, we can easily calculate this variable, which is kind of the phase information with the 2 different type of the quantum dynamics. So now we have three and 4 algorithms, 3 and 4. This case, that 3 have another or energy different term, but 4 is just for the phase information. So let's take a look at the results. Okay, so the x-axis is the annealing time. As I mentioned, shown in a previous study, the shorter annealing time is preferable because we want to solve the problem in a shorter time. And you see all of the algorithm, they have a good performance compared to the quantum annealing because quantum annealing doesn't work for short annealing time. But the performance of the quantum annealing increase when we increase annealing time. And unfortunately, two of those 2 curves in red and blue and green decrease when we increase time, so which is not good. But you see the algorithm 3 and 4 in purple and light green, you see that so always it show the better performance compared to the quantum annealing, even the longer annealing time. So it seems a good observable we choose. And in short annealing time and long annealing time, so as you see in the previous slide, the algorithm 3 and 4 works pretty good. then I want to test this. This is a kind of new concept. We combine like quantum annealer and quantum circuit. We don't know such kind of hardware, so I just want to simulate in a quantum circuit. And we need to estimate how many measurements we need. And in many cases, in a quantum circuit, they just set the 1K or 10K or 1 million. They set to for experiment. But in this case, the sensitivity analysis, we have to conduct the hypothesis testing on the which direction we should apply the counter-diabatic term. So we borrow the concept of the statistical testing, so we can estimate the right number of the shot. After estimation, we realize that. So the original QGO just utilize the quantum annealer. The short number is around 10K. But if we combine with quantum circuit, it will be more than 1 million. So this is the so this is a weak point for this algorithm. But anyway, I tested the most simple algorithm, the first algorithm. And the result, simply I can share that the number we get from the experiment and the number we predict from the mathematics seems a good agreement. So that our algorithm will work if we have a combination of the like D-Wave and IBM or whichever. And what we learned is that in the last bullet. So this study shows example that the quantum processing of quantum data. So quantum data in a first algorithm, DAQG1, or no, the original QGO algorithm process the classical processor. But now we calculate the phase information. That is, we need another quantum circuit. In such case, there's a room to improve the performance. I mean, when we apply the phase information, we have better results compared to the just simple the classical, the difference of the energy. Okay, so I have another 25 minutes. Okay, so I move into the another topic. So this is what originally I want to show here today. So as I'm working for industry, car industry, so the CAE stands for the computer-aided engineering. That is the tool to design products. So yeah, computer, we see computer. So what if we replace with computer by quantum computer? That is what I want to know. And also, there's a very similar activity called AI for science. So I want to share what is the similarity or what we should do with the community of the AI for science and quantum community. So again, the CAE stands for the computer-aided engineering. So that is a design automation for industrial products. And here, automation means automated loop. So here, so we start the initial design of the product and simulate with finite element method or the simulation method, and we get the data. We know the good point or good bad point of this design, and also just but computer or algorithm understand how to improve this design and repeat or modify the design, change the conducting another simulation and repeat that process again and again without human decision. So for the company who makes the equipments, so we want to push just one button to start this process, and a day after, we want to have the best blueprint of the product. That is what we want to have. So I hope in the future the quantum computer can help for this purpose, or accelerate or empower the CAE by quantum computing. So first, but there's a very similar approach, or there's a big similarity between that kind of the CAE and AI for science. So I will introduce. So this is my old paper when I worked for bioinformatics field. So the typical scientific study, I think, is a study from literature or database to make a prediction model, or not in mathematical, but some kind of idea to make hypothesis. And we can predict some, let's say, the drug candidate, and we test it. And if it works, okay, write a paper. This is a very conventional type of science. But after the AI era, we need more effort to do something. That is also the automation, or to leverage that kind of the infrastructure to have more big scientific discovery. So we need this loop here. So this kind of idea is not just I invent. No, actually, many people are thinking very seriously, and there are several white papers from like Japan and US and OECD, and some communities. This is Nobel Turing Challenge. Turing Challenge is kind of the big AI challenge. I think now it's we or AI scientists win the challenge, and Nobel Turing Challenge is another challenge. In the future, the AI win the Nobel Prize. That's why the Nobel is here. Or more simply, AI for science. That help or accelerate the science by AI technology. And why I'm talking this is so not just AI, but also we should apply the quantum computing for this purpose for science. And very interestingly, so quarter century ago, you know, all nature journal have the one page of the sci-fi story in every issue. And this is by Ted Chan. He's a famous sci-fi writer. And he talked about the kind of AI scientists in the future. And AI scientists invent many scientific findings, and human can't understand because they are really, really smart. And so that is kind of the beyond human cognitive limitation. Yeah, that will happen or not, I don't know, but we can try. So another concept I thought is in So the Feynman said, you know that I can safely say that nobody understands quantum mechanics. So we or many physicists believe that is correct. Oh, yeah, but in the era of the AI, or AI scientists may say, I can fairly say that the mechanic machines may grasp quantum mechanics. That is another challenge, or that is the same as the challenge of the Nobel Turing challenge, I think, for physicists. So that is the concept of the AI for science. And the current status, I want to compare AI for science and the CAE, what we are doing with the CAE tools. So you may know that the automation level of self-driving, I put here in right side, and their extreme goal is, yeah, actually, we don't have to drive. The car itself drives. But we still don't have this. This is something the current status is around here, level 3. And also, we can define the similar level of the automation science from level 1 to level 5. And we are here. And this means if we define that the optimization loop very strictly, clearly to computers, it can be automated. For example, this is a seminal paper from the Rosking and his team. That what they did is, so first read many papers, or they utilize database of the life science, and after that they can make, or computer can make a novel hypothesis and conduct experiments, not by human but by robot. And the robot conducts an experiment, and we get the data and analyze the data. That means we add extra data or knowledge, and combining the existing knowledge and the new knowledge, we or computer have another hypothesis to be tested by this robot. So repeating this process, we may have the new finding without human. And this kind of the process we also realize today by using the CA tool. So we want to simulate something like this. So we want to make the car body right as much as possible, but we want to prevent the humans from the car crash. So that we want to optimize. And again, this kind of the CA tool automated the simulation and data science and optimization. So this is very similar to what the Rosking team did. So this is the level 3 of the automation in science and engineering. So how we move forward to quantum? So this is a simplified version of what we did in science and engineering. The more simply, we conduct simulation, and after that, we have the data, so we do the machine learning. After that, we conduct optimization. So, you know, each step, those tasks, we know that we have some algorithm for quantum simulation and quantum machine learning and quantum optimization. So my talk is about the quantum optimization, how this can be help for automation, science, and engineering. So after publishing the seminal paper of this field, so I will talk about the optimization of the combinatorial black box optimization. So we conduct the simulation experiment, but before conducting that, we don't know the relationship between the input variable x and the output of the y. So we have to learn from data. That is a setting of the black box optimization. And there's a two seminal paper in this field. It published in 2018, and 5 or 6 years past. We have several POC studies in medicine, optics, chemistry, electronics, data science. Yeah, so that is what we, including me, showed. This is a promising approach. And in this approach, we utilize the Cubo solver, including quantum annealer. That is the possible way to accelerate the quantum technology for engineering and science. So I will show some example we conducted. So this again, I'm in the car industry, so and my company make a car equipment like something like this. So this is a PCB board mounted on an engine room. So we need many mounting holes. But we want to reduce the number of holes because it costs. So we conduct the FEM simulation here in here, and we have data, or we have several data. We build a Cubo form. That is a machine learning part. And once we have a Cubo equation, so we optimize it. But this Cubo is not perfect because the number of data is initially it's limited. So after optimizing this Cubo, we will conduct another simulation, and we add the more data to generate a better Cubo formula. And similar approach we tried for the noise filter design. We have inductor or capacitor here. And so as the high frequency signal, so we have to design the pattern in a copper layer of the printed circuit board. That means, so topologically, these two are same. But when we input the high frequency signal, so the characteristics are very different, and this is optimized pattern. But using the industrial standard method, the topology optimization. And we applied our method of the black box optimization. We have the similar pattern. That means this approach can be replaced, no, the existing tool or topology optimization algorithm can be replaced by black box optimization. Okay, so I talked about the replacing one component of that optimization loop, but we want to think more or go further. So if we have to put two algorithms in two positions, for example, hypothesis generation, this is kind of the optimization part, and the simulation part. So this is not directly associated with this concept, but the former presentation, digital analog quantum computing, combining the quantum annealer and followed by the quantum circuit is kind of align this concept. And what we showed in a previous part, we saw that the quantum data, quantum processing perform better than quantum data and classical data processing. So this digital analog quantum computing one possible platform to support this quantum CAE concept. And not just so that case, we apply two algorithms out of three. But this is very small study, but they conduct or put all of the elements in a single algorithm, starting from the parallel simulation, the quantum simulation, and they finally find the best optimal structure. So for small case, there's a POC study already. And so just this is an example of what we are doing now is, so there's many products or many field of the simulation. We basically need the quantum version of the simulation. So in this field, people are working hard to invent the quantum version of the simulation algorithms. This is one example. This is a quantum algorithm for radiative transfer equation. Okay, so this is a summary. This is the final slide. So, so we see that the AI for science and quantum CAE, there's many similarities. That is basically the closed loop without human decision. And now, very interesting what I want to say in the last slide. So AI and quantum computing for science and engineering is the area what we focus on. That is, I think. And interestingly, including our institute, this is AIST's group, the global research, blah, 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 and quantum AI. So we combine the quantum and the AI. And also, we know there are many the groups having the quantum and AI in their name. So, okay, that's it. Thank you very much.
So, Kadowaki-san, thank you very much for very impressive talk. So now session is open for discussion and comments. So any question, comment from audiences? So I have a question there. Your last part of your talk, so you show that the example of the quantum CAE based on the quantum data. And the quantum, yes, quantum data and quantum processing give better performance than the quantum data classical processing. That's quite interesting. But are there any specific example using the quantum data and the quantum processing for this kind of the quantum CAE scheme? So I cannot imagine that what kind of the example can be used for this kind of the.
Thank you for the question. So far, I don't know the really good example on this, but I think that we'll see, or we already see some acceleration improvements of the machine learning area, the quantum machine learning area. They're working to run the quantum data by quantum circuit. That is, I think, one of the hot area. That concept is not only just the quantum data, the quantum machine learning with the quantum data, but we can generalize that concept to pass through the hypothesis generation, the optimization, and simulation in this case. But also in this case, you see the data generation is kind of simulation, and the model generation is the machine learning. That part, many people are working on this, but there are some areas we can focusing with the model generation, the machine learning to hypothesis generation. That part, how we can combine two algorithms. Yeah, but at this point, there's no study on this, I guess.
But in the future, yes, someone will find some specific example for this kind of the scheme work very well. So I hope that it will work. So anyway, so any question? Yes, Nishimori-sensei, please.
I also have a question on this slide. Can you elaborate more on this data on the right bottom side? What problem did you try to solve? And what are the axes, and in what sense do you say quantum is better than quantum classical? I didn't catch it. You may have said it, but I missed it.
Okay. This plot actually show that concept. That was in the previous slide deck. So basically, we can compare with the blue line, the QGO, and others, especially like you can focus on the algorithm 3 or 4 in purple or light green. In a longer annealing time, the algorithm 3 and 4 performs better. That process the quantum data by quantum circuit. So quantum data processing. But the original QGO, it processes the data from D-Wave or quantum annealer classically. So focusing on that point, I say that quantum.
So you implemented this problem onto the real hardware. So you realized these protocols on the IonQ device?
No,
No.
no. This is just a simulation.
I will ask in details.
Okay, so we'll later
I'm-
discuss on this point during lunchtime. So any question or comment? Okay, so if not, thanks to the Kadowaki-san and also all the speakers.